go through it quickly. So remember, cosine is x, sine is y, tangent's y over x. Secant is the reciprocal answer of cosine, and cosecant is the reciprocal answer of sine. So here we go, sine at 210. So go to 210, find the y value. What'd you get? Negative 1/2. Agreed? Yeah. Cosine of negative 30 degrees. Guys, 30 degrees is going up, negative 30 degrees is going down. Or you can find the coterminal angle and it will fall in the same spot, right? So we're looking at right here is negative 30 degrees, or 330 if you found the coterminal, same thing. So our cosine is √3/2. Did you get it right? Sweet. Okay, sine of pi fourths. Now remember, a lot of you kind of said, well, what's pi fourths again? So if I create a 45-degree angle like this, boom, I just created a 45-degree angle. Didn't that open up on the arc from here to here? Yeah. Well, the pi fourths is just the length of the arc. Well, pi fourths and 45 degrees are the same thing. One's the angle, one's the arc length. So at pi fourths, what's the sine value? The y value, guys, √2/2. Did we get it? Okay, cosine of 3 pi fourths. Do we agree? Because we can go over it if we need to. If not, we're just going to keep going on. Okay, the tangent at 2 pi. Remember, tangent's y over x, so right here is 2 pi. 0, 2 pi, same thing. 0 divided by 1. 0 divided by 1 is 0. If we would have had 1 divided by 0, that would be, nope. Can we divide by 0? No, but it is a good thought. That's actually what I bet a lot of us would put on accident is 0. So just a quick reminder, dividing by 0 is not okay. That's not what we had. I'm just making a point. Okay, awesome. What's the tangent at negative pi fourths? Negative 1, because it would be the y divided by the x. Anything divided by itself is 1, and then one of them was negative. Yeah. All right, the secant at 210. So guys, this is how you do it. You say, I'm going to find the cosine. Look, S and C. Remember how we talked about their opposites go together? So cosine at 210 is, the cosine at 210 is √3/2, isn't it? So you flip it, 2 over √3. And then you'd say that answer is just not an appropriate answer. We've got to rationalize our denominator. Oh, sweet. It's negative. Okay, perfect. Good fix. So you multiply by √3 over √3, like Elise is saying. And so we get negative 2 √3/3. Who got that one right? Nice job. Nice job. But you got it right. You just didn't simplify your answer. Okay, the cosecant at 120. So you say, I'm going to find the sine at 120 and then take that answer and flip it. So the sine at 120 is √3/2, isn't it? Then you flip it. So 2 over √3, which is 2 √3/3. Sweet. Any questions on that? Okay, moving on. So we're going to try to get as much done as possible in class again today. So today we're going to be switching and getting into more radians and degrees. Now remember, this is what's important. By definition, what is a radian? Well, we have briefly talked about it. So the angle, a central angle is created when you start at the center of the circle and open up on an arc. So let's say that I opened up a 90-degree angle here. The radian is the physical distance of the arc from here to here, the actual length of the arc. So right here is the degree measure, here's the length of the arc. So the length of the arc of 90 degrees is pi divided by 2. I want you to take your calculator. That's an actual length. Take your calculator and do pi divided by 2 so you can see. So that really is just a decimal, an actual physical length. What's pi divided by 2? What decimal? 1.57. So guys, literally the distance from here drawn to here is 1.57 in length. Does that make sense? This is how mathematicians write it as a pi radian. Right here is what's called a decimal radian. That's just taking and finding the actual distance, not just leaving it as a pi. So if we have a central angle and we open up on an arc length, this is the radian, this is the degree. But they're the same, it's just one is the angle measure, one's the length of the arc that the angle opens up on. Does that make sense, everybody? Yeah. Okay, so how do we convert? How do we convert from, for example, 90 degrees to get pi halves radians? Well, this is how you can convert. You take the degree measure, and you multiply by pi over 180. That will change it to its radian. the physical distance. It will take it from its degree and change it to its radian. Now I want you to think about it. Halfway around the circle is 180 degrees, which is also the same thing as pi. So we're just actually multiplying by a fancy 1 because they're the same thing. One's the radian, one's the degree, but they are the same thing. So we're actually just multiplying by a fancy 1. So here's how I remember what goes on top, because everybody always forgets, should I put pi on top or degree on top? So everybody, if you have a degree up here, you need the degrees to cancel out, so you put the degree part on bottom. So let's convert 45 degrees to its physical length, its arc length, because if I said to you, all right, I have a circle here, and I want 45 degrees worth of distance, you'd say, well, how much distance is that? Well, let's find out. Here we go. So we convert it by multiplying by pi over 180 degrees. So then we know how fractions work. We multiply straight across. So we have 100, look, our degrees cancel out. So we have 45 pi over 180. Take your calculator, because I want the simplified pi answer. Don't type pi in yet. Do 45 divided by 180, math, enter. Good, 1/4. That became a 1, that became a 4. So does everybody see how 45 degrees is arc length is pi fourths? This is its radian form, this is its degree form. We got 1/4, which is pi fourths, everybody. Okay, so that's how we can convert it and find the length of the arc instead of the angle it opens up on. So now, everybody, an engineer, if I said, okay, cool, so I have pi fourths worth of distance, an engineer would say, stop being cool, just tell me how many dang inches or feet. So now you would type in pi divided by 4, ready, go. Give me the decimal, like an actual answer here. Cool. So I want you to give me both. This is what's called the pi radian, and this is the decimal radian. A mathematician would want this answer. An engineer would want this answer. All right, let's convert negative 240 degrees to radians. So we'd multiply by pi over 180. Type into your calculator. Negative 240 divided by 180. Math, enter. Because we're simplifying our answer. Thank you. This became a 4, this became a 3. Does everybody see how it's negative 4 pi thirds? And then our decimal answer would be type in negative 4 times pi, hit the pi button, divided by 3. What decimal is that? Did you say negative 3.188? I can't hear you. Negative 4.18. Okay. There are times when it would be better, like in real world problems, when if we're trying to find a distance, it's better to have a radian than a degree. And there are times when instead of having a radian, it would be beneficial to have a degree. So now let's convert from, let's say we're given a physical length, a radian, and we want to know its equivalent central angle, the angle instead. We want it in its degree form. To convert from radians to degrees, you'd multiply by 180 over pi. Now think about why we would now put pi on bottom. If we have a pi up here, we need our pi's to divide out if we want to write it as a degree. So does everybody see why instead now we're going to put pi on bottom here? Okay, cool. So let's convert pi 6 into its degree form. So we'd say we're going to take that and multiply by 180 degrees over pi. So now by hand, I can literally divide out the pi's. Now do 180 divided by 6. 30 degrees. So that would be the angle that opened up on. Okay, cool. Now here's what always used to throw me off. I remember back in the day. If I see 1.8 radians, people always say, well, how do I convert that? So everybody listen very carefully. Didn't we just say that this was the pi radian, but then we can actually go through and find the decimal radian? Well, the decimal radian already has pi multiplied into it. It's just not written pretty. It's already multiplied in. So there is a pi in there. It's just already been put in there. It's already been multiplied in. So you do the same thing. You say, I need the pi's to divide out. So I'm going to multiply by 180 degrees, just like we did before, divided by pi. Now up here, notice the math's worked out where we can divide out pi by hand. Right here, we can't divide out pi by hand, so our calculator will do it for us. So you would type into your calculator 1.8 times by 180 and then hit divided by pi because we couldn't divide it out by hand. Yep, perfect. 103.14 degrees in measure is 1.8 radians in length. Cool. So let's go to 36. So this is when it would be useful to take something and convert it from a radian to a degree. We know how to draw degrees, and drawing the degree is a lot easier than trying to figure out where to draw the radian. Way easier. So it says right here, 36. Draw this angle in standard position. Remember, standard position means on an XY chart. So draw an XY chart. And we have to have an initial side. Now, everybody, figuring out where 2 pi ninths is going to be hard. So let's just convert it to degrees, because then that's easy to graph. So we'd say, instead of that radian, I want it as a degree. So I'd multiply by 180 over pi. Once again, pi's on bottom, because I can then divide them out. So then you do 2 times 180 divided by 9 in your calculator. 2 pi ninths is what degrees? 40 degrees. So now look how much easier it is to graph a degree than a radian. Do you all agree? We don't need to. Where's 40 degrees? Right here, right, everybody? Yeah. So you go, I went positive 40 degrees, so draw your arrow just like we did last time. We went 40 degrees, which is the same thing as going pi ninths. Pi ninths was just this length, from here to here. You get what I'm saying? Well, we've drawn in 40 degrees, and then we could give a hint. This is 50 degrees, if we needed to give a hint. So why not? All good? So that's a time, really the only time we'd rather have a degree rather than a radian is if we're graphing, because really physical length for story problems is always going to be better than a degree. All right. So on number 33, let's see if you could do this one by yourself. It says determine the quadrant or the axis where the terminal side of this angle lies. So ready, set, go. Where does that angle fall? In what quadrant or on what axis? Figure that out. Is that what you got? It's what? What angle did you converted it to a degree? 206 degrees roughly. So that helps me picture where it is better. You'd say, okay, well, it's somewhere over here. This is 270, so it must be in quadrant 3. Now, everybody, if you have, this is an XY axis. Let's pretend that it fell on 90 degrees, for example. You'd say, okay, it fell on, yes, exactly. It fell on the Y-axis between quadrant 2 and quadrant 1. Does that make sense? If it falls right on an axis, you'll say it's on the X-axis between quadrant 2 and quadrant 3. Or it fell on the Y-axis between quadrant 2 and 1. And just so I know exactly where it falls. Okay, do the problems. The more you get done in class, the less homework you have. Ready, go. Before we move on, I'm going to give you time to practice and understand that. I do want the mathematician answer, the pi, and I want the decimal answer too. I don't think a lot of you have picked up on this fact. Okay, if I go positive 2 pi thirds, that would be going over here to that point, correct? Yes. That's a distance. Now, if I said go negative 2 pi thirds, you got to go that same amount of distance, but downward. So look, that was how many dots up? 1, 2, 3, 4, 5. So the negative amount would be 1, 2, 3, 4, 5. Boom. Right there is negative 2 pi thirds, everybody. Yeah. Okay. Okay, so this is honestly where math is used in the real world a lot for arc lengths and circles. Because think about it, there are circles in the real world everywhere, meaning like, for example, sewer ponds are circles, right? If you have to build a fence around a sewer pond, you need to know how much fencing is taking place, and you've got to know how much fence to buy, and there's a lot of things. There's so many swimming pools and so on. So everybody, this is the length of the arc. So that means if we look at this circle, and I have a central angle opening up on this arc, didn't we learn that if we find the radian of 30 degrees, that would be this length? That's what a radian, by definition, is the length of the arc that central angle opens up on. So let's convert it. You'd say, okay, to find the length of the arc, I take 30 times by pi over 180, which is pi 6. So this distance from here to here is pi 6 in length. Well, now I've drawn a smaller circle, and I say find the length of the arc from here to here. So it's the same thing. But guys, can that be possible that they're actually the same length? They are definitely not, correct? I measured it out. Like those are definitely not both the exact same length. Look at the picture here. This is real world math. So what's making the difference here? The size of the radius. The radius. So let's say this was 10 centimeters long. Let's say this was 2 centimeters long. Well, to find the length of the arc, you would take the radian that the central angle opens up on, and you times it by the radius. So times by 10 centimeters. So literally, that would actually, if we took and measured out 10 centimeters, we then drew a circle, and then I said to you, okay, how much length is between a 30-degree angle? How many centimeters? You would find, if you did this, it would actually be the real amount of centimeters. So, yep, so, yeah, exactly. She just put two and two together. So the length of the arc is, you just said, radius times the angle. Radius times theta is the length of the arc. Yes, she just came up with the formula herself. So the length of the arc is you take the radius and you times it by the angle. But it has to be the radian, the physical length of the angle. Does that make sense, everybody? So let's figure out how many centimeters. If this is really 10 centimeters radius, how many centimeters is between here and here? So wouldn't that be this? 10 pi 6 centimeters? So then you'd say, okay, 10 pi 6 centimeters, which simplifies to be 5 pi third centimeters in length. And then an engineer would say, okay, stop trying to be cool here as a mathematician. How many centimeters is it actually? So that's when you would type it into your calculator and give me the decimal answer. How many actual centimeters here? 5.12, just over 5 centimeters. You guys, this would really work. Like, we should test this out one day. I promise it really works. So that is literally how many centimeters is between here and here. Okay. Yep, it would come out right. We should do that one day. So then you could say, okay, we have a radius of, you could literally grab a piece of string, do 4 feet worth of string, and you could go around in a circle, and then you could actually find out how many feet is in that. It's cool. We'll do it. So let's do this one. So it was pi 6, but then what changes it is we've got to multiply by the radius. So now we have this 2 pi 6 centimeters worth of length, which is pi third centimeters worth of length, which is exactly about 1.0 something. Type it in, pi divided by 3. How many centimeters is on this one? 0.4. So it's a little over 1 centimeter. That is truly how it is found in the real world, like lengths around circles for fencing and things like that. So that is the formula. The length of the arc is equal to radius times theta, as long as the angle theta is in radians. Anytime we're dealing with physical length, we need the radian because that's by definition what a radian is. So sometimes the angle will already be written as a radian, you're good to go. But sometimes if it's written as a degree, you got to convert it. So let's look at 21. It says, find the length of the arc that this central angle opens up on. So you say, okay, the length of the arc is my radius, which is already written as a radian. Lucky for us, we don't even need to convert it. You guys see? Times by 4, which is 28 pi over 8, which simplifies to be, which is inches. So, which is how many, like what simplified? 7 pi half, guys? 28 divided by 8. Do you get what I'm doing? Yeah. Because the mathematician would want this answer. 7 pi half inches, and then the engineer would say, how many inches? Like, cut to the chase. How many actual inches is located there? So then you would say, which is about 11 inches. So I want mathematician answer and engineer answer. Oops, I should have only circled right here because we don't want the unsimplified math answer. Does that make sense, everybody? Yeah. Just radius times theta. That's all you got to do. Okay, there you go. Do these problems. More likely what you'll be asked, they're not going to just say, find the length of the arc on an ACT. They're going to give you a problem like 24. So let's read it. It says, suppose a windshield wiper has a length of 22 inches and rotates through an angle of 110. What distance does the tip of the wiper travel as it moves once across the windshield? So isn't that just asking for the length of the arc? So draw yourself a picture. Like, think about it in the real world. Say, okay, here's my window on my car. A windshield wiper goes like this, back and forth, back and forth, back and forth. It said that was 22 inches long. It said it rotates through an angle, so it's going to stop at some point and go backwards, right? Of 110. So, and then it's asking us how much distance does the tip of the wiper travel? So when we find one distance here, isn't that the length of the arc? The length of the arc. So you say, okay, length of an arc is equal to radius times theta, but that's 110 degrees. We need it in radians, so it's a physical length, not a degree measure. Yep. So you'd go off to the side and say, okay, I need to convert that to radians. I want physical length of 110 degrees. So then that's 110 over 180, I believe, is 11 pi 18ths. So then this is 11 pi 18ths, but that's not enough, right? We've then got to take into consideration our radius is 22 inches. We say the length of that arc is 11 pi 18ths, and then we've got to times by the radius of 22 inches. So now we know. Perfect. And it's a story problem, so, I mean, with a story problem, we're going to just want a decimal answer, really. So that would be 42.2 inches. That's what they're going to ask you on the ACT, something like that, to see if you can, I mean, that is just asking you to find the length of the arc, not any different. But they will never just say, given 110 degrees and a radius of 22, find the length of the arc. They're going to make you draw a picture. Okay, cool. So I want you all on 27. This is one that I definitely could see something similar to this on the ACT. It says, the minute hand of a clock is 8 inches long. The minute hand of a clock is 8 inches long. So right here, about 8 inches, right? It says, what distance does it travel in 10 minutes? So look at a clock here. Here is 0 minutes, 5, correct? 10, right? We could keep going. This is 15. This is 20. We get the picture. So I'm splitting this up, though. I'm just going to keep going for my own benefit. I'm splitting it up. So it says, what distance does it travel in 10 minutes? So think about it. Wouldn't that be from there to there? So this is asking for the length of the arc, isn't it? So now you're going to have to figure out, you'd say, okay, to find the length of the arc, I need a radius, which we know, and then I need to figure out what theta is. So let's see if you guys can use your brains to figure out what degree measure is that arc being opened up on. Ready, go, think. Okay, just so for my video, so we have now figured out that we did 360 and we divided it by 12 sections, and so each section is 30 degrees. So that's 30 degrees, so is that is 30 degrees. So it says, how much does it travel in 10 minutes? So 10 minutes would be that amount of distance, which would be 30 degrees plus 30 degrees. So our theta in this one is 60 degrees. So you'd say to find the length of the arc from here to here, I need to convert 60 degrees to radians. So you'd multiply by pi over 180, which is pi thirds. And you'd say, so the distance from here to here is pi thirds. But now I got to times by the radius of 8 inches. So that would be 8 pi third inches, which is approximately 8.4-ish inches. Hey, so, to finish the worksheet, the only one you should be crossing out, and you could do it, I bet, some of you, is 23. But I bet some of you could do it.